Welcome back to Calculus 2. This is part 2 of our lecture on trigonometric integrals. Still dealing with the first topic, powers of sine and cosine and their integrals. All right, now we left off in the last part dealing with examples where we had sine and cosine to various powers, and provided there is at least one odd power, we split off one of the factors from the odd power, be it a sine or cosine factor. Pulling off a single factor from an odd power leaves you with even powers. And then for the even powers, we apply a combination of Pythagorean identities to rewrite everything with our appropriate substitution. Well, we're going to address right now what to do if we have only even powers. In other words, for this example, here we have sine and cosine both to the second power. There are no odd powers here. We're going to have to kind of modify our approach. This is a separate case in the standard way to teach this section, which we kind of do have to account for. All right, so let's suppose we did try our previous method, seemed to work before. Let's see what maybe goes wrong. Let's try splitting off a single factor of cosine. All right, we're going to leave sine squared as is. We'll deal with rewriting the remaining cosine x by itself. But if we split off a cosine x factor, using that for du, if du is cosine, our u must have been sine. All right, so far this seems to be kind of the same as the previous examples in part 1. We now just have to rewrite everything in terms of sine. Well, it's a little bit tricky here because that is leaving us in the integral with a factor of cosine, not cosine squared. Recall your Pythagorean identities apply to squared trig functions. Now we can modify that. You might be thinking, aha, I can take a square root of both sides. And you can. It gets a little tricky due to the plus or minus, but there is a bigger issue. If you were to use this version, you would end up rewriting that integral, that remaining cosine of x factor, with your substitution u equals sine of x. You would get this complicated radical integral. The integral of u squared times the square root of 1 minus u squared. Earlier, when we covered our arc length and surface area integral formulas, we mentioned at the time, due to the presence of square roots, those integrals were difficult to deal with and evaluate. And the same is true now. So what we have done is basically taken an original integral and presented it and rewritten it and rewrote it as one that's more complicated. Now, this is not mathematically wrong, but it's certainly not helpful. So our approach of trying to split off a cosine factor and then rewrite everything as before seems to fall apart here. All right, now there is a separate way to kind of proceed through this. And this is where the half angle reduction identities come in. And the key here, since we have cosine and sine squared, only even powers, through repeated application of these reduction identities, we can reduce the power down slowly, eventually down to just single first powers of cosine functions. All right, notice what happens though with these formulas. As you reduce the power, the angle doubles. All right, if you need to, pause the video, copy down these half angle reduction identities. In the case that you don't know them, we're going to need these to go through this example. With that in mind and out of the way, let's go ahead and get to example 3. We're going to evaluate the antiderivative, the indefinite integral of sine squared times cosine squared. Now, this question, most of the work is just basically at the pre-calculus level, using the half angle or reduction identities repeatedly to rewrite both sine squared and cosine squared as reduced powers. So if you want, pause the video, give yourself an attempt, rewrite sine squared times cosine squared with a repeated application of the reduction identities. We'll check in maybe about 2 minutes. All right, so let's go through and just do the rewriting part. All the work here, let's take it line by line. So at the top there, we're just stating what the half angle reduction identities are. And we're going to apply both of them since we have a sine squared and cosine squared factor. All right, so I apply the half angle identities and reduction identities to both of them. I have factors of a half from each identity. I can combine that out front as a single 1/4 factor. And then the 1 minus cosine of 2x times 1 plus cosine of 2x, we can expand that. It's basically a factored version for a difference of squares. The outer and inner terms will cancel. If you fully expand that, you'll get 1 minus cosine squared of the angle 2x. Cosine of 2x times cosine of 2x is cosine squared of 2x. All right, now the angle originally was x. We had sine squared and cosine squared of x, and now we have cosine squared of 2x, the angle doubled. What we do, again, since we have a power of cosine here, cosine squared, we apply the reduction identities yet again. The version we're going to use is recognizing it's cosine squared of 2x. 2x is the angle, double 2x to get 4x. So if you're careful with that, inside the parentheses, right next to the identity in red, we replace cosine squared of 2x with its rewritten version using the reduction identity again. Just be careful with parentheses. If you distribute that negative 1/2 through there, still within the larger parentheses, we have 1 minus 1/2 minus 1/2 cosine of 4x. We can combine 1 minus 1/2, that's positive 1/2, and then inside the parentheses, we can factor out a factor of 1/2. And if you pull that out front, 1/2 times 1/4 will give you that factor of 1/8. Now again, this is all kind of pre-calculus level. Might be a little bit foreign since you probably maybe haven't used the half angle or reduction identities since your pre-calculus course, but there's really no calculus here. It's all just algebraic rewriting using your trigonometric identities. What we've done is we've taken our original function and have rewritten it in a form that's easily integrated. Here in the parentheses, we have 1 or 1 dx will integrate to x, and cosine of 4x, we can apply our 1/a shortcut. Special case for substitution, we know an antiderivative for cosine. The inner linear expression, 4x, when we integrate, we'll get a factor of 1/4. If you need to, go back and rewatch our lecture on substitution where we introduced the 1/a shortcut. Basic antiderivatives with linear expressions, ax plus b inside. All right, so here we rewrote our function in a form that's easier to deal with. Now we can actually do calculus. Now we can integrate it. So now we're integrating the alternate version, 1/8 times 1 minus cosine of 4x, and we can integrate that term by term. All the work here, probably 90% of it, is in applying the half angle reduction identities. And your antiderivative here, we have that constant multiple 1/8 out front, and then inside the parentheses, 1 integrates to x, cosine of 4x integrates to 1/4 sine of 4x. And we're done. Now, depending on what you're referencing, if you are referring to some like online integral calculators, other references, there might be alternate versions which apply identities to rewrite sine of 4x. This is one of many different equivalent versions. This one is the most simplest from what we arrived at from our version applying the reduction identities multiple times. Okay, now you can see this example is really tedious. Probably anything beyond squared powers of sine and cosine, anything beyond a total power of the fourth power of sine and cosine combined or sine and cosine individually becomes really tedious. For instance, if this were instead sine to the sixth times cosine to the sixth power, this would be awful. We'd have to apply the reduction identities a lot more times. But it can be done. All right, so that is it for example 3. That concludes everything we would cover for the first type of integral, powers of sine and cosine. With that out of the way, we're going to proceed to part 2, integrals for powers of tangent and secant. These get a little more complicated because the derivatives of tangent and secant are a little more complicated. All right, so let's get to part 2. Again, in the standard way to teach this topic within a Calculus 2 course, most professors probably resort to telling their students to just memorize the different cases. Do this if m and n are certain combinations of being even or odd. That works. It'll get you through the course, but I find that approach students lack seeing how everything fits together. Again, to try to get you to see that, our unifying idea for all of our trigonometric integrals is we split off factors for the differential du. And then we work backwards. Whatever we split off for du, we then determine what the u should be from that. Why does this get more complicated? Because the derivatives of tangent and secant are more complicated than the derivatives of just sine or cosine. Now, if you understood thoroughly the first part, integrals for powers of sine and cosine, this is just the logical extension of that. But since the derivatives of tangent and secant are a little more complicated, it seems a little more complicated. I realize it is, since for many students in the calculus sequence, derivatives of other trig functions like tangent and secant don't come readily as sine and cosine in their derivatives. Okay, so if you take a look at the derivatives, the answers, they're secant squared and secant x, tangent x. That tells you what we're going to split off. Since the differential du is basically a derivative, we're going to split off a secant squared factor or a secant tangent factor. In the first part, integrals for powers of sine and cosine, we only split off sine or cosine because the derivative of sine or cosine is just sine or cosine. Here we work backwards. If we split off a secant squared for du, the u should have been tangent. If you split off a secant x tangent x factor for du, your u should be secant x. So notice how it all fits together with our unifying idea, provided you're comfortable with these little more obscure trigonometric derivatives. But if you've been going through the calculus sequence with your Calc 1 course pretty recently, these probably are pretty familiar to you. Okay, now we do expect from the examples we covered in part 1 for integrals of powers of sine and cosine, we might have to use a Pythagorean identity while going through some of these integrals and their evaluation. So just make sure you know the Pythagorean identity for tangent and secant squared. 1 plus tangent squared equals secant squared. Now, a hint we'll give is typically for the standard examples we'll be looking at for this part, whatever you split off, the remaining factors typically get rewritten using Pythagorean identities. A way to check if you've split off things correctly is what remains after you split off if it contains only even powers. at least for the basic integrals pertaining to powers of sine and cosine and powers of tangent and secant. All right, with that out of the way, let's go ahead and get to an actual example. Take a look at two of them. I think some of you can probably make an attempt at these. Think of what your derivatives are of tangent and secant. See if you can split off appropriate factors, splitting off either secant squared or splitting off secant tangent. Those are the derivatives of tangent and secant. With what remains not split off, see if you can then rewrite that using Pythagorean identities. Now, I realize some of you might be lost because derivatives and things related to tangent and secant probably aren't as familiar as sine and cosine. So if you'd like, pause the video and make an attempt. If not, continue. I'll pause for a few seconds in the case that you do want to pause the lecture and actually attempt these first. All right, either you just waited for me to resume or you made an attempt. Let's go through part A. Now, in order to kind of keep both ideas in mind, we want to split off something for du while having the remaining factors being able to be rewritten using Pythagorean identities. And what's going to work here, since we have secant to the fourth and tangent to the sixth, we can split off a secant squared factor. The remaining terms, tangent to the sixth and secant squared, possibly can be rewritten since they are only even powers. We can rewrite them using Pythagorean identities if needed. So if we work backwards by splitting off a secant squared for du, just think what differentiates to secant squared? Tangent. So if du is secant squared, the substitution u must have been tangent. So here, this is pointing out by splitting off secant squared, we can complete the problem by doing a substitution u equals tangent of x. Du would then be secant squared x dx. All right, maybe with that as a hint, pause the lecture if you need to complete it. Maybe you can see where this is going. If not, we'll resume. All right, so now we kind of see what our substitution is. So we have tangent to the sixth, which we can rewrite as u to the sixth with this substitution. We have to rewrite secant squared in terms of tangent, and that's where your Pythagorean identity comes in. The version we're going to use is 1 plus tangent squared equals secant squared. So we can replace the secant squared kind of sandwiched in the middle of that integral. We can rewrite secant squared as 1 plus tangent squared. Our substitution here is tangent. So all the pieces fall into place. We split off something for the differential. We see what substitution we should make and what Pythagorean identity we're going to use. If you rewrite all your pieces, now everything falls into place. We're rewriting secant squared as 1 plus tangent squared. And the secant squared x dx factor at the end is du, which means u must have been tangent. If we convert everything from a trigonometric integral in x, convert everything properly, we should get tangent to the sixth converting to u to the sixth, in parentheses 1 plus tangent squared converting to 1 plus u squared, and then secant squared x dx converts to du. All right, at this point, we get a simple polynomial integral in u, and we can complete the question just by expanding that and integrating those powers of u using the power rule for antiderivatives. The last step is we back substitute our u, which was tangent x. All right, now before we go on to part B, I want you to try to see and think back to the examples we covered for part 1, integrals of powers of sine and cosine. This is very similar. It's only more complicated since the derivatives of tangent and secant are more complicated. But everything parallels those previous examples almost exactly. All right, now with part A here out of the way, maybe you feel more confident to make another attempt at part B. Before I advance to the next screen, maybe pause the video for here while part B is still on the screen. Try again if needed, integrating tangent to the 5th times secant to the 7th. We'll check in a few minutes if you're making a second attempt at it, having seen the work and understood part A here. All right, are you ready? Let's get to example 4B. All right, now again, keep in mind your intuitive ideas of what's going on. We split off something for du, and we try to rewrite the remaining expressions and terms using Pythagorean identities. Pythagorean identities only apply to squared trig functions, so we're going to need, with whatever we split off, to have even powers left over. Now, there's not a lot of possibilities here. Notice if you were to, like in the last question, try to split off secant squared, take off 2 factors from secant to the 7th, 2 powers less would leave you secant to the 5th, an odd power. Remember, we want the remaining terms to be typically only even powers so we can apply Pythagorean identities. So splitting off secant squared won't work, but splitting off secant x tangent x will, because tangent to the 5th reduces down to tangent to the 4th for what's left. Secant to the 7th reduces down to secant to the 6th. All right, and don't forget why this works. What you split off, whatever it is, here we're splitting off secant x tangent x. We reserve that for du. Remember your fundamentals. If your du is secant x tangent x, the trig function that differentiates to secant x tangent x must be secant x. That's telling us that we're going to make a substitution, u equals secant x. All right, now if u is secant, we can easily convert secant to the 6th as u to the 6th with our substitution. We would then have to convert and rewrite tangent to the 4th power, and that's where your Pythagorean identity comes in. Just be careful. The standard version for the second Pythagorean identity is 1 plus tangent squared equals secant squared. We need to solve that individually for tangent squared in terms of secant squared. So subtract the 1 to the other side, like we have here, to arrive at tangent squared equals secant squared minus 1. All right, if you got stuck on part B, maybe repause the lecture from here to complete it. If not, we'll proceed. I realize these secant tangent integrals are certainly a lot trickier. So let's continue. We apply our Pythagorean identity first by rewriting tangent to the 4th as tangent squared squared. Inside the brackets, we replace tangent squared with secant squared minus 1. Notice the external 2 still on the outside of those brackets. All right, with our substitution u as secant x, we can rewrite all the pieces accordingly. Inside the brackets, that'll convert to u squared minus 1 squared on the outside. Secant to the 6th converts to u to the 6th. And secant x tangent x dx converts to du. At this point, the hard part is done. and we get our resulting polynomial integral in U, which we can multiply, FOIL, expand to get a sum of a bunch of powers of U's. All right, so if you're just careful and FOIL or expand U squared minus 1 squared, and then distribute U to the 6th n, we get simple powers of U. Fully simplifying that, we get the integral of U to the 10th minus 2U to the 8th plus U to the 6th. And from here, the calculation, very easy, using the power rule for antiderivatives. To complete the question, back substitute U in terms of X. Here we used U as secant X. And we get, again, kind of an ugly looking expression. Typical answer for the antiderivatives in this lecture for trigonometric integrals, but maybe not as aesthetically pleasing as previous antiderivatives and answers. But that's aesthetics, that's philosophy. We're in a mathematics course, we'll save that for later. Okay, these were the basic integrals for tangent and secant and their powers. And at that point, we pretty much have, I'll say, probably 85% of all types of trigonometric integrals covered within that. Now, there are some other oddball examples, other types of trigonometric integrals, where those previous ideas of splitting off a factor for du might not work. That applies to basic integrals, integrals for powers of sine and cosine, and integrals for powers of tangent and secant. Now, integrating does get tricky. Integration is much more difficult than differentiation. It's said that integration is an art, whereas differentiation is a science. Basic product, quotient, and chain rule, you can calculate any derivative pretty straightforwardly. It's not at all apparent with seemingly simple integrals how you should approach them. Like what we have here, the integral of secant. Now, just to point out how tricky and difficult integration is compared to differentiation, maybe you've encountered how to solve this integral, or maybe not. A standard way to arrive at the antiderivative for secant is non-obvious. Now, maybe to the first mathematician that discovered this or invented it, maybe it was obvious because they're brilliant, but to most people and myself, it's not at all obvious why this trick will work. What we do is we multiply by 1. It's a well-chosen one, something divided by itself. What we multiply and divide by is secant x plus tangent x. And that is definitely not obvious, but it works. Now, again, maybe you have already encountered the antiderivative for secant. Maybe you've never encountered it. We're going to need it for some of these oddball examples in this lecture. How does this actually complete the problem and give you an antiderivative? Well, we can distribute that secant into the numerator of that fraction. You can rewrite that numerator then, fully distributing it, instead of leaving it factored, as secant squared x plus secant x tangent x. Now, again, the mathematician that first discovered or invented this trick, it might have been obvious where this was going. We then just make a substitution, u as the denominator, u as secant x plus tangent x. The derivative of that is exactly the numerator. So after a non-obvious trick, and then maybe a non-obvious substitution, we get a remarkably simple antiderivative in terms of u, the integral of 1 over u du. That integrates to natural log of u, and we back substitute our u, and we get the antiderivative, natural log of secant plus tangent x. Again, this was highly non-obvious, but it does point out that there are some certainly tricky integrals falling within this oddball case for trigonometric integrals, integrals that don't seem to fit the approaches for powers of sine and cosine or powers of tangent and secant. All right, now I hate to say it, but this is a good antiderivative to memorize, so that way you're never caught off guard again, either in our course or beyond. All right, now there's two that we're going to need for some of the questions you might encounter in the homework where maybe you have to integrate by parts, maybe some other ideas. We'll give some tips momentarily. Let's point out what those kind of antiderivatives, those integrals are, that I'd like you to just be able to quickly recognize and memorize. So the first tip, not really a tip, but just memorize these since they're a little tricky. We know the integral for tangent. We did that in substitution. It becomes negative natural log of cosine. Or if you want to be fancy, rewrite that as natural log of secant. From what we've worked through now, maybe for the first time, for the last few seconds, maybe you saw the integral for secant here for the first time. We now know the integral of secant, natural log of secant plus tangent. Again, highly non-obvious, but for certain questions in this set of examples that don't fit part 1 or 2, it's good to know these so that way you can quickly get through these oddball questions. All right, that's going to help for certain questions. A second tip is maybe, if it doesn't seem to fit the approaches for powers of sine and cosine or powers of secant and tangent, try to rewrite everything and certain expressions in the integral using Pythagorean identities. If that doesn't seem to work, your kind of approach of last resort, try to maybe rewrite everything in terms of sine and cosine. Recall from all 6 trig functions, there's really only 2 basic ones, sine and cosine. The 4 other trig functions, tangent, cotangent, secant, and cosecant, can be expressed as combinations of sine and cosine. So your, again, option of last resort, try to rewrite the integral in terms of just sine and cosine, and hope and pray, cross your fingers, that a substitution works. All right, let's take a look at least one last example just to get a taste for how all these tips work together. Our 5th and final example that we'll cover in detail is evaluating the integral of tangent cubed. All right, now this falls into the oddball category. It's not a strict integral of the form for powers of sine and cosine, and it doesn't seem to fit the obvious approaches for what we mentioned with powers of tangent and secant. Try one of those alternate tips we mentioned and see if that maybe gives you some ideas of how to approach this. Pause the lecture. We'll check in a few minutes. All right, hopefully you made an attempt. This one is not difficult, but it is a little tricky since it doesn't seem to fit our basic examples in part 1 or 2. All right, what's going to work here is, well, let's split off tangent squared so that way we can apply a Pythagorean identity. Your clue here is, well, one of the tips was we could try applying a Pythagorean identity, but the Pythagorean identities apply to even powers. So if we have an integral of tangent cubed, let me pull off 2 factors of tangent and then apply a Pythagorean identity. All right, so this seems like maybe it will take us somewhere. Let's see where that goes. Let's replace tangent squared with secant squared minus 1. Now, how we actually complete the problem is by recognizing basic antiderivatives that we know. If we distribute tangent through the parentheses to get the integral of tangent times secant squared, and then minus the integral of tangent, the last integral, the integral of tangent of x, we know that as negative natural log of cosine of x. That's one of the ones that I asked you to memorize, specifically for this example. So hopefully it would be kind of really quick for you to say, aha, I know the integral for tangent of x, negative natural log of cosine. The first integral, the integral of tangent times secant squared, well, provided you know your derivatives, your fundamentals, that's a straightforward U substitution. We'll choose U as tangent since the derivative of tangent is the remaining factor in that integral, secant squared. So you can use a U substitution to rewrite that first integral as the integral of U du, and then you integrate that to get 1/2 U squared. Back substitute, you get your antiderivative as 1/2 tangent squared. Put those two antiderivatives together, and we've completed the question. Now, there's plenty of other examples scattered throughout the homework that fall into this oddball case, don't seem to easily fit powers of sine and cosine or powers of tangent and secant. That's okay. With those tips, you probably have the tools to tackle them. All right, one of the last things I want to get to is how we incorporate definite integrals. It's very minor, as we've seen through previous topics. Let's just recall that this entire lecture is really based off of U substitution. What do we do with definite integrals with U substitution? Well, I've advocated to change the limits. So all we need to do here is just plug in our limits, 0 and pi over 2, to whatever substitution we choose. It's again only trickier since your basic trigonometric values for special angles might have been forgotten. But let's take a look at this example and see how we could approach it. It's very minimal compared to everything we've covered so far. All right, so we take a look at the integral. It's secant to the 4th, cosine to the 5th. This falls into our basic first integral type, powers of sine and cosine. We have an odd power, cosine to the 5th, split off one factor of cosine for your du. If du is cosine, your u must have been sine. And from here, we now know what substitution to make. We plug in our original x limits, 0 and pi over 2, to our substitution, u equals sine of x. Our new converted u limits, sine of pi over 2, that's 1, and sine of 0 is 0. This is everything that we've advocated with substitution already. It's just only now inside of a trigonometric integral problem. So if you rewrite that integral using your Pythagorean identity and all the other ideas we mentioned, you get the integral from 0 to 1 of u to the 4th times 1 minus u squared squared. And if you carry that out, you get a bunch of fractions. Your answer here can be combined as 8 over 315. The 315 comes from the factors 5, 7, and 9. All right, so definite integrals really are just converting the limits, which is what we mentioned with substitution all along. All right, now before we end, I realize this is really complicated. Trig is probably not that very exciting for you. I need to answer the standard question that all of you are thinking, what is this good for? Or what am I going to use this for? Well, there's a good answer. There's a place that you might encounter it rather soon in perhaps your P-Chem physical chemistry course, or if you get into upper level physics courses and deal with the electron orbitals for simple atoms, I'll say. Now the mathematics tends to get complicated, but powers of sine and cosine are related to mathematical functions called spherical harmonics. And that's probably the first place you might actually put that to use, which some of you might be getting to rather shortly. Hopefully that's a satisfying answer to, what is this good for? Where am I going to use this?